Hello everyone and welcome to our next lesson. This is part 1 of our discussion on heat transfer by conduction. But before we begin, we will first discuss the other modes of heat transfer. Let us begin with the differentiation of the different modes of heat transfer that we will be tackling throughout our entire discussion on heat transfer. Basically, we have three types, that is conduction, convection, and radiation. And all of these three modes of heat transfer differ greatly on the way of how they transport heat. In heat transfer via conduction, heat is being transported by the vibration of atoms or molecules. In conduction, the atoms or molecules do not move themselves. Instead, they are vibrating in place. And the faster the molecule vibrates, the higher its energy content. And it is this high energy content that is being transferred to its adjacent atoms. Okay? So as you can see in this illustration, the molecules that are directly subjected to heat from this Bunsen burner are vibrating faster than the molecules that are far from the source of heat. So what's happening is that the molecules at higher energy levels are transferring their energy to other molecules, which are then transferred to other molecules, and so on and so forth. So in heat conduction, heat always flows from a higher temperature to a lower temperature. Next is convection. As I've mentioned earlier, for conduction, the molecules themselves are not moving. They are simply transferring their energy to their neighbors through vibrations. But for convection, there is an associated movement of atoms or molecules. We call that a convection current. Convection can only happen in fluids. So when we say fluids, that encompasses both liquids and gases because they are free to move in convection currents. A warm parcel of fluid, be that a liquid or a gas, would tend to float or would tend to go up because it gets less dense, and a colder parcel of the fluid would tend to go down because it's more dense. It is this alternating cycle of rising and falling and rising and falling in fluids that results to heat transfer via convection. So if we will compare the rates of transfer of energy for convection and conduction, convection is faster than conduction because convection employs the movement of fluid. This has something to do with momentum transfer as well, because if the fluid is moving faster, then it can transfer a larger amount of energy. It also has something to do with laminar and turbulent flow. So we will be discussing all of those in a separate discussion. The third mode of heat transfer is radiation. Now, radiation is unique out of the three modes of heat transfer because radiation does not need any medium to transfer heat. Radiation is possible because of electromagnetic waves, and we all know that electromagnetic waves do not need any medium to propagate. This is the reason why the energy of the sun can always reach the earth even though the distance between the sun and the earth does not contain any matter because heat is propagated through radiation. Also, we will be discussing the entire topic of radiation in a separate video. Now, let's dive deeper into conduction. Throughout our lesson, expect that we will be deriving equations regarding conduction for different geometries. The basic principle of conduction is that molecules vibrate at a rate that is proportional to its energy level. When we say energy level, that gets translated to the temperature of the substance. So if a substance is at a higher temperature, we expect that its atoms are vibrating more. And if a higher energy atom is placed next to a lower energy one, the tendency is for some of the energy to be transferred from the higher energy to the low energy atom. This is the principle of heat conduction. Okay? Always remember that our transfer is from a higher temperature to a lower temperature. The phenomena of conduction is represented by Fourier's first law of conduction. As we have discussed earlier in our introduction to transport phenomena, we have here the rate of heat transfer Q divided by the heat transfer area A is equal to negative K, or thermal conductivity, multiplied by the gradient dt over dx, or the change in temperature with respect to position. Okay, so let's go straight to our first derivation exercise. We want to derive the equation for heat transfer through conduction for a tube of inner radius r sub I and outer radius r sub O, and inner and outer wall temperatures of Ti and To respectively. Assume that the inside temperature T sub I is greater than the outside temperature T sub O. So we are expecting that the heat will be transferred from the inside of the pipe to the outside of the pipe. And our starting point for this derivation will be Fourier's first law of conduction, that is Q over A is equal to negative K times dt over dx. However, we will be changing our variables here because this form of Fourier's law is designed for the Cartesian coordinate system, and our system described here should be using the cylindrical coordinate system. So our modification would be, this would become Q sub R because the flow of energy is in the radial direction. By the way, this is a cross-section representation of the pipe. And our gradient would no longer be equal to dt over dx. This should be changed to dt over dr because our temperature is expected to vary in the radial direction. Let us start by reimagining our system. So I have redrawn the system here, just a little magnified, for you to be able to see the inner radius r sub I and the outer radius r sub O. Now remember that we are looking at the cross section of a pipe. So we are actually face to face with its cross section, okay? In this case, heat is being transferred in the radial direction. That's why our Fourier's law of conduction would become Q sub R over A is equal to negative K times dt over dr. We are expecting the temperature to vary with respect to the radius. Now, all we have to do is to integrate this expression with respect to r, and then we will have an expression for the heat transfer. However, before we do that, we first need to define what is the area being pertained to in this equation. This area we are describing here is the perpendicular area to which heat is being transferred. So if heat is being transferred in the radial direction, the area that we are pertaining here is the surface area of the pipe. So the surface area of the pipe is dependent on its radius and its length. So we write the surface area of the pipe as 2 pi r L. Now notice that we have not decided if we are going to use r sub I or r sub O as our radius in the computation of the area. That's because r is an independent variable and that will be part of our integration. So if we substitute area to Fourier's law, we get Q sub R over 2 pi RL is equal to negative K dt over dr. Now let's separate the variables. We have a collection of the constants QR over 2 pi L multiplied by dr over r is equal to negative K dt. Now take note that QR here is constant. We are saying that the rate of transfer of heat through conduction is constant. Okay? Integrating, we have Q sub R over 2 pi L times ln of R, integration constants from the inside R sub I to the outside R sub O. Now, how did we decide that the direction will be from the inside to the outside? That's because the direction of heat transfer will be from the inside to the outside because the inside is at a higher temperature. Okay? That's the same with temperature. So on the right-hand side of the equation, we have negative K T, limits of integration from T sub I to T sub O. Substituting, we now have Q sub R over 2 pi L, ln of R sub O over R sub I is equal to negative K TO minus TI. Now, rearranging and simplifying this equation, we now have the expression for the rate of heat transfer Q sub R. That is equal to 2 pi KL over ln of R sub O over R sub I times difference in temperature T sub I minus T sub O. So I have removed the negative sign in the right-hand side of the equation by switching T sub I and T sub O. So therefore, this is now our expression for the rate of heat transfer through the wall of a pipe. Okay? Now, if you will remember, we have previously discussed that the rate of transfer is always equal to the driving force over the resistance. We can then rearrange our equation to fit this description. So our rate of heat transfer is already Q sub R. Our driving force is the difference in temperature, that is T sub I minus T sub O. That means that everything else remaining is our term for the resistance. So we write Q sub R is equal to the driving force T sub I minus T sub O all over ln of RO over RI over 2 pi KL. We now say that our resistance term is ln of RO over RI over 2 pi KL. Remember that this is always our resistance to heat transfer via conduction if we are talking about cylindrical systems, or specifically if we are talking about tubes and pipes. Okay, this resistance term will be very important later because if you have resistances in series, then these are what we are going to be adding. Okay, let's proceed. We now have here the general energy equation. This is another differential equation that looks complicated, but we will be able to simplify this. So the first term here represents the amount of heat energy going in and out of a given boundary. It's the thermal conductivity multiplied by the Laplacian of T. We call this symbol the Laplacian. We will be expanding this later for the three major coordinate systems. The second term, Q, here is called heat generation. The third term is called the dissipation function. This is the Greek letter phi. And the dissipation function has something to do with momentum transfer. Because remember, momentum transfer enhances heat transfer. However, if we are talking about conduction, generally we can assume that the dissipation function is negligibly small. And on the right-hand side of the equation, we have our time derivative of the temperature. So just as what we did in momentum transfer, if we are assuming that the heat transfer is steady state, then this term here is 0 because it's a time derivative. Okay, so we have here several assumptions that will simplify the general energy equation. First, if the thermal conductivity is constant, then this term simply becomes K times the Laplacian of T. Now, for majority of our problems, we will be assuming that K is constant, or we can simply get the average thermal conductivity for a specific temperature range. Because keep in mind that the thermal conductivity of substances are functions of temperature. Next assumption, we will be assuming that the heat capacity at constant pressure is equal to the heat capacity at constant volume for solids. Because when we are dealing with conduction, mainly we will be studying solids. Next, we are assuming negligible dissipation function and no heat generation. Therefore, the general energy equation reduces to Fourier's second law of conduction. This is this equation here. So we are just retaining the time derivative of temperature and the Laplacian of the temperature. Remember that we have already discussed that alpha, or thermal diffusivity, is defined as K over rho times Cp. Therefore, our general energy equation reduces to the partial derivative of temperature with respect to time is equal to the thermal diffusivity multiplied by the Laplacian of temperature. So this simplified general energy equation looks like this in the different coordinate systems. For the rectangular coordinate systems, we have this equation. That is, the time derivative of temperature is equal to the thermal diffusivity multiplied by the second derivative of temperature with respect to x plus the second derivative of temperature with respect to y and the second derivative of temperature with respect to z. And these are also the same equation in cylindrical and spherical coordinates. So far, we have encountered two equations regarding conduction, Fourier's first law and Fourier's second law. Okay? For the derivation of temperature profiles, we are going to use the Fourier's second law. Just like what we did with momentum transfer, wherein we derived velocity profiles, in here we can also derive temperature profiles of materials. Let's start with this one. For steady-state conditions, the general heat equation becomes alpha, or thermal diffusivity, multiplied by the Laplacian of temperature is equal to 0 because the time derivative of temperature would be equal to 0 for steady-state conditions. We want to derive the steady-state temperature profile for a flat wall, as shown here, from T1 to T2. Also determine the heat flux equation. So our system in this case is a wall. This is a cross-section of a wall. And as you can see here, T1 is higher than T2. Therefore, the transfer of energy will be from X1 to X2. Okay, let's derive the temperature profile. For this derivation, we will start with the general energy equation. That is, the partial derivative of temperature with respect to time is equal to alpha times the second derivative of temperature with respect to x plus the second derivative of temperature with respect to y and the second derivative of temperature with respect to z. Now, let's try to simplify this equation. If we are assuming that the heat transfer is steady state, then the first term becomes 0 because it's a time derivative. And if we are assuming that the heat transfer is through one dimension only, meaning it's only being transferred in the x direction, then there's no need for the y and z derivatives of temperature. Okay, we are left with the equation alpha times the second derivative of temperature with respect to x is equal to 0. This is our simplified general energy equation. This equation is further simplified to be the second derivative of temperature with respect to x is equal to 0. Okay, we can now integrate this expression. The first integration would yield the derivative of temperature with respect to x is equal to a constant, C1. And the second integration would yield us the temperature profile. Temperature is equal to C1x plus C2. This is our general temperature profile. However, to make it specific, we have to solve for the values of C1 and C2 using boundary conditions. If we are assuming that the thickness of the slab is L, therefore we can write two values for x. That is x is equal to 0 on the left side of the wall, and that is x is equal to L for the right boundary of the wall. Okay, let's use the first boundary condition. At x is equal to 0, our temperature is equal to T1. If we substitute the boundary condition to our temperature profile, we have T1 is equal to C2 because x is equal to 0. Therefore, we now know the value of C2 to be T1. Next, we substitute the second boundary equation. At x is equal to L, the temperature is equal to T2. Substituting to your temperature profile, we have T2 is equal to C1L plus C2. C2 is T sub 1. And then we can manipulate this expression to get the value of C1. C1 is equal to T2 minus T1 over L. We now have the value of the constants C1 and C2. Next, you can substitute the values of C1 and C2 to our temperature profile. We now have T is equal to, that's T2 minus T1 over L times X plus C2 T1. This is now our temperature profile. Now, let's examine the form of our temperature profile. What type of equation is our temperature profile? If you take a look at the independent variable x, its exponent is 1, meaning that our temperature profile is linear. If you take a look at our illustration, you can see that the distribution of temperature across the slab or across the wall is linear. Okay? This means that the temperature linearly varies with respect to position, and it is varying with a slope of T2 minus T1 over L. Now, you can imagine that if the difference between T2 and T1 is large, then that means that your slope would be larger and the steepness of the profile would be larger as well. So that is how we use the general energy equation to derive the temperature profile of a system. Let's try to connect this with Fourier's first law. So for this system, Fourier's first law is written as Q sub x over A is equal to negative k times dt over dx. This is for rectangular system. Now, what area are we talking about here? The direction of heat transfer will be from T1 to T2, and the perpendicular area will be the area of the wall itself. Okay? So let's first leave the area as A, and let's evaluate the differential dt over dx. So if you take the first derivative of the temperature profile with respect to x, we get dt over dx is equal to T2 minus T1 over L. We now have the temperature gradient dt over dx. If we substitute this back to Fourier's first law, we have Qx over A is equal to negative k times T2 minus T1 over L. And if we rearrange this equation to get the rate of heat transfer, we get Qx is equal to T1 minus T2 all over L over Ka. This is again written in a familiar form, that is rate of transfer is equal to driving force over resistance. Our rate of heat transfer is Q sub x, our driving force is T1 minus T2, and our resistance in this case for a slab or for the rectangular system is the thickness L over K over area of transfer. Or in other cases, we can also write this as delta X over Ka. Okay, so far we have derived the resistance term for cylindrical system, and for the rectangular coordinate system, we also have derived the resistance. And we are going to use those resistance terms in our next examples. So let's proceed. Let's have this example. A furnace wall is composed of 3 layers. 10 centimeters of fire brick, you're given the thermal conductivity 1.56 watts per meter per Kelvin, followed by 23 centimeters of kaolin insulating brick with thermal conductivity of 0.073 watts per meter per Kelvin, and finally 5 centimeters of masonry brick, thermal conductivity of 1 watt per meter per Kelvin. The temperature of the inner wall surface is 1370 Kelvin, and the outer surface is at 360 Kelvin. What are the temperatures at the contacting surfaces? So this is our first example wherein we will be applying our derived equation for the rate of heat transfer in rectangular coordinates. This is the illustration of our problem. So this is a wall of a furnace and it's a 3-layer wall. At the innermost, we have fire brick with a given thickness of 10 centimeters and thermal conductivity as shown. We have the middle layer kaolin with a given thickness of 23 centimeters, and the outermost layer is masonry brick, 5 centimeters thick with a given thermal conductivity. The temperature inside is 1370 Kelvin, and the temperature at the outside surface is 360 Kelvin. What we are being asked in this problem is to determine the junction temperatures of the surfaces. So we have two junction temperatures or temperatures at the contacting surface. I have labeled them T sub 1 and T sub 2 in the figure here. T sub 1 is the temperature at the junction of the fire brick and the kaolin, and T sub 2 is the temperature at the junction of kaolin and masonry brick. Now, before we can solve this problem, I have written here our derived Fourier's first law for this slab system. We have the rate of heat transfer Q sub x is equal to the driving force T sub I minus T sub O all over the resistance delta x over Ka. However, this single equation pertains to the entire system, meaning if we are talking of the driving force, that would be the inside temperature minus the outside temperature, and the overall resistance would be the sum of the resistances of all of the 3 layers. Now, if we want to consider the resistance of each layer, which we need to because we are solving for the junction temperatures, we first have to represent this in terms of resistances in electrical circuits. An appropriate and equivalent diagram of what we have here would look like this. The first resistance or the first resistor pertains to the first layer, that's delta x1. The second resistor pertains to delta x2 or the kaolin layer. And the third resistor pertains to delta x3 or the masonry brick layer. Now you might notice that I have drawn these 3 resistors in series because they are in series. If you take a look at the transfer of heat, it's from T sub I to T sub O because T sub I is greater than T sub O. So the general direction of heat transfer is from the inside of the furnace to the outside of the furnace. If you take a look at the arrow of Q sub x, it is passing each layer one at a time in series. That's why we have represented the resistances in series. Okay, so let's call this resistance 1, resistance 2, and resistance 3. Now the question is, where in this new diagram is our T sub I and T sub O, or the inside and outside surface temperatures? T sub I would exist here at the beginning, and then the outside temperature T sub O would exist immediately after R3. The way on how we interpret this diagram is that in order for us to transfer energy from the inside to the outside, we first have to go through 3 resistances in this particular order, from R1 to R2 to R3. That's why it's called resistances in series. The next question is, where in our diagram are the junction temperatures T1 and T2? Remember, T1 exists between the fire brick and the kaolin brick. That's between R1 and R2. So therefore, we can say that T1 exists here in the middle of delta x1 and delta x2. And T sub 2 or T2 exists here in the middle of delta x2 and delta x3. Okay, so these 2 representations are equivalent. We call this an equivalent circuit. Okay, next is, how do we apply Fourier's first law to our equivalent circuit? Now, I have mentioned earlier that this Fourier's first law that we have written here applies to the entire system, that is from T sub I to T sub O. But what we have to remember is that the rate of heat transfer in here is constant. Okay, always remember that. So the rate of heat transfer is constant. The area is also constant. What's only changing is the thickness of the material. So if the overall rate of heat transfer Q sub x is constant, we can say that if I go from T sub I to T sub O, that is already Q sub x. And if I only consider the points from T sub I up to T sub 1, I would only get Q sub 1 as my rate of heat transfer. However, Q sub 1 is still equal to the overall rate of heat transfer Q sub x for the entire system. So therefore, we write the overall rate of heat transfer Q sub x, let's say for example, is equal to Q sub 1, meaning the rate of heat transfer passing through the first layer only. That's also equal to Q sub 2. That's still equal to Q sub 3. And then we can write Fourier's first law for each of these heat terms. That is how we will be able to solve for T1 and T2. So let me first erase some of this. Going back to the problem, we can write the total rate of heat transfer Q sub T is equal to T sub I minus T sub O all over the total resistance, R1 plus R2 plus R3. Now, what is our resistance R? Remember that we have already derived our expression for the resistance for this system of slab, that is delta X over Ka. That means that our R sub 1 is simply delta X1 over K1 times A. Remember, area is constant. Our R2 is equal to delta X2 over K2A, and our R3 is equal to delta X3 over K3A. Okay? We substitute all of these resistances to our overall rate of heat transfer, and we can solve for its value. Substituting, we have T sub I, 1370 Kelvin minus T sub O, 360 Kelvin, divided by R1 is, delta X1 is 10 centimeters, so I will be converting everything to standard SI units so that we won't have any problem, okay? So delta X1 is 10 centimeters, that is 0.1 meters, divided by K, 1.56, times A. I will be assuming that the area of heat transfer is 1 square meter. We can assume that because area is constant. Next, delta X2 is 0.23 over 0.073 times 1. Plus for the last layer, that would be 0.05 over 1 times 1. Okay? We can solve for the value of Q sub T. That will be 1370 minus 360 divided by 0.1 over 1.56 plus 0.23 over 0.073 plus 0.05 over 1. So our overall rate of heat transfer is 309.36 watts. Remember that our unit for the rate of heat transfer is watts or joules per second. Okay, so what's next? We now have the value of the overall rate of heat transfer. We can now use this in the individual resistances to determine the junction temperatures. So let me first erase some of this. We have the relationships Q sub T is equal to Q sub 1 is equal to Q sub 2 is equal to Q sub 3. Now, if I'm going to write our expression for Q sub 1, remember Q sub 1 is the rate of heat transfer for the first layer only. Our driving force is T sub I minus T1 because those are the boundary temperatures of the first layer, divided by the resistance encountered in the first layer, that's simply R sub 1 or delta X1 over K1A. That would be my expression for Q1. Now remember that we have earlier solved for the overall rate of heat transfer, that is Q sub T or Q total, and that's equal to Q sub 1. So we can now substitute everything to this equation. We have 309.36 is equal to T sub I is 1370 minus T1 over delta X1 is 0.1 over K1 is 1.56, and we have assumed that area is 1 square meter. As you can see here, we can now solve for T1. Solving for T1, we have 1370 minus 309.36 times 0.1 divided by 1.56. Okay? I have rearranged this equation mentally. So T1 is 1350 Kelvin. The next step for you is then to determine if this answer makes sense. Remember that the inside temperature in the furnace is 1370 Kelvin, and then after passing through the fire brick, the temperature was reduced to 1350 Kelvin. So based on our diagram, T1 should be less than T sub I because it is encountering some resistance. Next, let's try to solve for T2. When solving for T2, we simply have to change our equation from Q sub 1 to Q sub 2, and then our driving force will also change. If you take a look at our resistance diagram, our driving force will now be equal to T1 minus T2, and our resistance would become delta X2 over K2A. So it's the same process. And remember, Q2 is still equal to Q total. So that's still equal to 309.36. We will just be changing our numerator and denominator. T1, which we have already solved, is 1350 Kelvin minus T2, which we are trying to solve, over delta X2, 0.23, over K2. K2 is 0.073 times area is 1. We can now solve for T2 is 1350 minus 309.36 times 0.23 divided by 0.073 times 1. Our T2 is 375 Kelvin. Now again, let's check. Does this answer make sense? T2 should be less than T1, but it should be greater than T sub O. At this point, we know that our answer makes sense because 375 Kelvin is in between 1350 and 360 Kelvin. So our temperature profile would really look like this as pictured in this diagram. Okay, so from T sub I to T sub 1, it would slightly decrease. From T1 to T2, it would greatly decrease. And from T2 to T sub O, it would again slightly decrease. Now, what are the contributors if the decrease is large or small? The number one contributor is, of course, the thermal conductivity. If you have a high value of thermal conductivity, you would have a lesser value of delta T. If you take a look at the fire brick, the thermal conductivity is 1.56. That is larger than the thermal conductivity of the second layer, which is 0.073. That's why in part, T sub I minus T1 is less than T1 minus T2. Or that's another way of saying that the temperature drop between T1 and T2 is larger because the thermal conductivity of kaolin is smaller. Of course, the thickness of the layer also affects the rate of heat transfer. And in this case, our second layer is thicker compared to the first layer. That's why the second layer also experienced a larger temperature drop. So this is how we solve problems for resistances in series. Okay, you first draw your equivalent resistance diagram for you to be able to understand the problem before you can proceed to the Fourier's first law. Let's proceed. Let's answer another example. A double pane insulated window unit consists of two 1 cm thick pieces of glass separated by a 1.8 cm layer of air. The unit measures 4 meters in width and is 3 meters wide. Under conditions where the extreme outside temperature of the glass is at negative 10 degrees Celsius and air at 27 degrees Celsius is adjacent to the inside glass surface, with H sub I is equal to 12 watts per square meter per Kelvin. We want to determine the inside glass surface temperature and the rate of heat transfer through the window pane. The air gap between glass panes may be treated as a purely conductive layer with K is equal to 0.0262 watts per meter per Kelvin, and thermal radiation is to be neglected. Now, let's first acknowledge that there is something new with this problem. We have a value of H sub I. H sub I here is referred to either as the convection coefficient, surface coefficient, or more specifically, it's the heat transfer coefficient of convection. Now, what do we do with this value? We simply convert this to another resistance and we add it to our equation. And here is the representation of our system. So we have two layers of glass, and in between those layers of glass is a layer of air. Now keep in mind that the given 27 degrees Celsius as the inside temperature pertains to the temperature of the air inside, and not the inside surface temperature of the glass. So we have to make a disambiguation between the temperature inside and the surface temperature of the glass inside. We will be denoting that as TSI with the letter S signifying that it's a surface temperature. Okay? Also, if you read the problem again, you would see that the negative 10 degrees Celsius pertains to the outside surface temperature of the glass. That's why we have written that here as TSO is equal to negative 10 degrees Celsius. We are given the values of delta X1 up to delta X3. We are also given a value for the heat transfer area, that is 4 by 3 meters or 12 square meters. And the new value that was given to us is the surface coefficient or the heat transfer coefficients inside. H sub I is equal to 12 watts per square meter per Kelvin. Take note of the units of H and of K. The units of H or the heat transfer coefficient is watts per square meter per Kelvin, while for the thermal conductivity, it's only watts per meter per Kelvin. Okay? Do not confuse those two units. Now, before we proceed with the problem solving, we first need to determine the thermal conductivity of glass. Remember that it was not given in the problem, so we have to search for its value. And let's take a look at its value from our handbook. So we can find that data in Chapter 2. Under transfer properties, we want the thermal conductivities of some materials for refrigeration and building insulation. Let's take a look at this table, table 2-326, and look for glass. For the entries of glass here, we have several types. We have borosilicates, window glass, soda glass. So let's use window glass because we are using the glass in our example as a window pane. The thermal conductivity of window glass, as shown here, ranges from 0.3 to 0.61. Now, since it is given as a range, what we're going to do is to simply take the average between these two values to get an average value for the thermal conductivity of window glass. Okay? So let's just say that the middle value between 0.3 and 0.61 is 0.45. And take note of the units of K. The units are given here. That is BTU per hour per feet per degrees Fahrenheit. Now, our next problem is to convert this collection of units BTU per hour per feet per degree Fahrenheit to our SI units watts per meter per Kelvin. For this purpose, there are conversion factors given in our handbook for us to have an easier time converting. Let's look for those factors. Those factors are given in Chapter 1, Table 1-4. Let's look for thermal conductivity. Okay, here we have the conversion factors for thermal conductivity. On the first row here, we have the units in English system. On the second row, we have the units in the SI system. And this is the factor that we need to multiply in order for us to convert. So our obtained value is in BTU per hour per feet per degrees Fahrenheit. We want to convert it to watts per meter per Kelvin. Therefore, we should multiply the value by 1.73. So that makes for an easy conversion. Let's go back. 0.45 BTU per hour per feet per degrees Fahrenheit multiplied by 1.73 should give us a value of K1 and K3 already in terms of watts per meter per Kelvin. That's 0.78 watts per meter per Kelvin. Before we proceed to writing Fourier's first law, let's first convert our diagram to an equivalent resistance diagram. Let's first count how many resistances are we encountering in the heat transfer. We have 3 resistances due to conduction. Those are the 2 layers of glass and the layer of air in between those glass layers. But we have a 4th source of resistance in our system, and that is the air inside of the room. That's why we are given the value of H sub I. So if we have 4 resistances in series, we can draw it like this. And we can label the inside temperature, Ti, and we will label the outside surface temperature as TSO. The first resistance is due to convection. It's not due to conduction. That's because the air inside is also offering some resistance to heat transfer. We will be discussing resistances due to convection in our next lesson. But for now, let's first accept that the resistance due to convection can be written as 1 over HA. This is different from our resistance due to conduction. For the next 3 resistances, these are all due to conduction. R2, R3, and R4 are all delta X over Ka. If we write our overall rate of heat transfer, that is Q sub T, is equal to inside temperature Ti minus outside surface temperature T sub O all over the sum of the resistances. That's R1 plus R2 plus R3 plus R4. Okay? Summation of the resistances. In the problem, we are asked to solve for the inside surface temperature of the glass, that is TSI. However, we cannot find that value unless we solve for the overall rate of heat transfer. So let's do that first. That would be T sub I minus TSO. So that is 27 converted to Kelvin, that is 300 Kelvin, minus negative 10 degrees Celsius is 263 Kelvin, all over the sum of the resistances. So the first resistance due to convection, that is 1 over H times A, 12 square meters, plus for R2, that is delta X, 0.01, divided by KA, K is 0.78 for glass, times area, 12 square meters, plus for the layer of air, delta X2, 0.018 over 0.0262, the thermal conductivity of air, times area, 12, plus the final layer of glass, 0.01 over 0.78 times area, 12. Solving for Q sub T, we have 300 minus 263 over 1 over 12 times 12 plus 0.01 over 0.78 times 12 plus 0.018 over 0.0262 times 12 plus 0.01 over 0.78 times 12. Our overall rate of heat transfer, 557.79 watts. Okay? Now we can solve for the inside surface temperature of the glass. For this purpose, we have to use Q1. So we write Q1, which is also equal to Q sub T, that is 557.79 watts, is equal to delta T. Our delta T for Q1 is T sub I, 27, that is 300 Kelvin, minus TSI over the resistance due to convection, that is 1 over HA, 1 over 12 times 12. From here, we can solve for TSI, that is 300 minus 557.79 over 12 times 12. So the surface temperature of the inner glass layer is equal to 296 Kelvin. Let's try to interpret if it makes sense. So Ti is at 300 Kelvin. TSI, as we have determined, is at 296 Kelvin. And at the very end, TSO is at 263 Kelvin. So it should make sense that TSI is in between the values of Ti and TSO. Okay? This example is basically the same as our previous example. The only difference is we are now introducing the resistance brought by convection. In this problem, we only considered the convection of the inside air and we did not consider the convection at the outside air. But should there be a value for the convection coefficient at the outside, you simply add that as another resistance in series. Okay? I will be showing you more examples of these types of problems, including problems involving resistances in parallel as well as combination of series and parallel in separate videos. Okay? For now, let's proceed. Let's now discuss conduction with heat generation. Earlier on in our discussion, we assumed that there is no heat generation within our system in order to simplify our general heat equation. But in this case, we are interested what happens to your system if there is already heat generation. This is now our general energy equation. If it's still steady state, therefore all time derivatives is 0, there is still no dissipation function. So the only thing that's left in our general energy balance is alpha times the Laplacian of temperature plus the heat generation term Q dot over rho times Cp is equal to 0. We are going to use this equation to derive the temperature profile and heat flux equation for a cylindrical wire with uniform internal heat generation Q dot. This is a familiar system to us. For example, this happens in electrical cables. When electricity goes through cables, it generates a little amount of heat, and that heat generation can be constant. So that is what we are trying to model in this case. Let's derive the temperature profile. Here is our simplified general energy equation, and at the middle here, I have written the definition of the Laplacian of temperature in cylindrical coordinates. Now, keep in mind that our system is a long cylinder, it's a wire, wherein the heat generation is uniform, and we are modeling the changes in temperature with respect to position. When I say position, we are referring to the radial position r, because we are assuming that the temperature at the axial direction z is constant. So this is another case of unidirectional transfer. If we are only considering the radial transfer of energy, then the Laplacian will be simplified by canceling the terms pertaining to the changes of temperature with respect to rotational position theta and axial position z. Both of these terms are 0. What we are left is this term, the second derivative of temperature with respect to position r, plus 1 over r times the derivative of temperature with respect to r. We can then substitute this equation to our general energy equation, and then we can go from there to derive the temperature profile of the system. Okay? Don't forget that alpha is always k over rho Cp. And then let me transfer the other term to the other side of the equation. Negative q over rho Cp. It is apparent at this point that rho and Cp will cancel, and we will be left with the equation, the second derivative of temperature with respect to radial position r, plus 1 over r times partial of T with respect to r is equal to negative heat generation Q over thermal conductivity K. This is now our working equation. The problem with this equation is we cannot solve it through the separation of variables because this is a second-order linear differential equation. What we can do is to simplify this in order for it to become a linear first-order differential equation. How do we do that? Let's represent F as the derivative of temperature with respect to R, such that we can change the second derivative of temperature with respect to R now becomes the first derivative of F with respect to R. Substituting, we have first derivative of F with respect to R plus 1 over R times F is equal to negative Q over K. This is now a first-order linear ordinary differential equation. How do we solve this? We first recognize that it looks like the form dy over dx plus py is equal to q. And for these types of differential equations, we can define an integrating factor lambda, such as this is equal to e raised to the integral of p dx. In our case, our differential is r, so this will become dr, and this will be equal to e raised to the integral of p, that is 1 over r dr. The integral of 1 over r dr is ln of r, so our lambda becomes e raised to ln of r, which simplifies to simply r. Our integrating factor is r. Okay? Now we can write our general solution to this differential equation as f is equal to the integral of lambda multiplied by q dr all over lambda. Substituting, we have the integral of lambda, which is r, multiplied by capital Q, in this case represented as negative heat generation over thermal conductivity, dr all over r. Integrating the numerator, we now have negative q over k times r squared over 2 plus c1 all over r. Simplifying, we have negative q r over 2k plus c1 over r. We now have solved for the value of f. But remember, we have represented f as the derivative of temperature with respect to r. So we can substitute it back, and we now have the derivative of temperature with respect to r is equal to negative QR over 2K plus C1 over R. Let me first erase some of this and then we can continue with the integration. Okay, we now have this equation. Derivative of temperature with respect to R is equal to negative QR over 2K plus C1 over R. Before we integrate this expression, we can already substitute a boundary condition so that we can determine the value of C1. A very good boundary condition in this case would be at the center of the cylinder at R is equal to 0. At the center of the cylinder, we have a finite value of the temperature gradient partial of T with respect to R. So it's not 0 and it's not infinity. We don't know the value, but we're going to write that this is a finite value. If you take a look at our equation here, if I substitute the boundary condition R is equal to 0 to our equation, that would result to the last term here, C1 over 0 becoming infinite. And if a term would cause the entire equation to become infinite, it's better to just set C1 is equal to 0 such that our entire equation will not be equal to infinite. So by setting C1 is equal to 0, we are ensuring that the value of the temperature gradient partial of T with respect to R remains finite. Okay, so C1 is equal to 0. We will be left with the expression partial of T with respect to R is equal to negative QR over 2K. And now we can integrate. Integrating this expression, we get our temperature profile T is equal to negative Q R squared over 4K plus C2. This is now our temperature profile. Now, if we are given any value of the temperature at the surface of the cylinder, we can solve for the value of C2. However, in this case, we are not given any value, so therefore, we will just have to leave this equation with the constant C2. Okay? However, this constant C2 will also be removed because we need to determine the rate of heat transfer through this system. If we go back to Fourier's first law, that would be QR over A is equal to negative K times dt over dr. Again, this is a cylindrical system, so the area will be the lateral surface area of the system, 2 pi RL. And then we just have to look for the value of dt over dr, but we have already identified that earlier. That is the first derivative of temperature with respect to R, negative Q dot R over 2K. We can substitute this. We have QR over 2 pi RL is equal to negative K times negative Q dot R over 2K. K cancels. We will be left with QR is equal to 2 pi RL times Q dot times R over 2. 2 cancels. We now have QR is equal to pi R squared L times the internal heat generation Q dot. This is now our rate of heat transfer for a cylindrical element with uniform internal heat generation. Okay? Now, since we have derived it here, you can now use this equation to determine the rate of heat transfer for such kinds of systems. Let's try to use this derived equation in the next example. A cylindrical nuclear fuel element is 10.16 centimeters long and 10.77 centimeters in diameter. The fuel generates heat uniformly at a rate of 51.7 times 10 raised to 3 kilowatts per cubic meter. The fuel is placed in an environment having a temperature of 360 Kelvin with a surface coefficient of 4,540 watts per square meter per Kelvin. The fuel material has a thermal conductivity of 33.9 watts per meter per Kelvin. For the situation described, evaluate the following at steady state. First, the temperature profile as a function of radial position. Second, the maximum fuel temperature. And last, the surface temperature. And end effects may be neglected. This is our representation of the problem. We have our cylindrical fuel element. It is a rather short cylinder with the diameter almost being equal the length of the cylinder. So it was stated in the problem that we can assume that end effects can be neglected. What we mean by that is that we can neglect the heat transfer through the ends of the cylinder. That is the top end and the bottom end of the cylinder. Therefore, we will only be focusing on the radial transfer of energy in our cylinder. However, this problem does not only rely with conduction, the other half of the problem deals with convection as well, as we are given the surface coefficient at the outside, that is 4,540 watts per square meter per Kelvin. Also, we are given the surrounding temperature because the fuel element is surrounded by a fluid, and that fluid is at 360 Kelvin. Take note that we are not given the surface temperature of the cylinder because we are to solve for the surface temperature of the cylinder. Okay? First, before we go to our required, let's first take a look at our rate of heat generation term, Q. This is given as 51.7 times 10 raised to 3 kilowatts per cubic meter. And we see that it is already in power per unit volume. What we only need to do now is to convert kilowatts to watts. So therefore, we have our Q as 51.7 times 10 raised to 6 watts per cubic meter. Okay? This makes it easier for us later when we substitute the values. So let's begin by using our derived equation for the rate of heat transfer in the system. That is Q sub R is equal to pi R squared L times the heat generation Q. From here, we can already solve the rate of heat transfer via conduction. So we write QR is equal to pi times the radius is half of the diameter, 0.1077 meters, over 2, quantity squared, times the length of the cylinder, 0.1016 meters, times heat generation Q, 51.7 times 10 raised to 6 watts per cubic meter. If you take a look at the cancellation of units, square meter times meter would cancel with the cubic meter at the denominator. So therefore, we will be left with the unit of watts for Q sub R. Solving, we have pi times 0.1077 over 2 quantity squared times 0.1016 times 51.7 times 10 raised to 6. We have a value of 47,852.6 watts. Now, what is the importance of this value of the rate of heat transfer? This rate of heat transfer will be equal to the driving force over the resistance. And we know that the resistance term is made up of two terms. The first term is the conduction within the cylinder, and the second term is the convection of the fluid outside of the cylinder. From that equation, we can easily solve for the surface temperature of the cylinder. If we are going to draw an equivalent resistance diagram for this system, we can draw it as such, wherein the first resistance is encountered by conduction. The second resistance is encountered via convection. The first temperature I shall be calling T sub C, and that is the temperature at the center of the cylinder. The junction between R1 and R2 is the surface of the cylinder, that is T sub S. And then the final temperature is the temperature of the surroundings, which is given as 360 Kelvin. Now, as we have mentioned earlier, the rate of heat transfer remains constant in every step of this process. So we can use the latter half of the process wherein we are going to consider the surface temperature and the surrounding temperature as our temperature gradient, while our resistance would solely come from convection. So we write Q sub R, or this is also equal to Q sub 2, referring to the second resistance, is equal to the temperature gradient, surface temperature minus surrounding temperature, all over the resistance. We have mentioned earlier that the resistance due to convection is simply 1 over H multiplied by the area. The area that we are referring to here is the lateral surface area of the cylinder because again, we are neglecting the effects of the top and bottom end of the cylinder. Okay, we define the lateral surface area of the cylinder as pi dl. Therefore, we can substitute that into our heat equation. This becomes HO times pi dl. We can now substitute our given. So this is equal to 47,852.6 watts, equal to, we are solving for the surface temperature. We are given the surrounding temperature as 360 Kelvin, all over 1 over H is 4540 watts per meter per Kelvin. And then times pi times the diameter 0.1077 meters times the length of the cylinder 0.1016 meters. So rearranging this equation, we can directly solve for the surface temperature of the cylinder. We solve that as 47852.6 divided by pi times 4540 times 0.1077 times 0.1016 plus 360. So we determine that the surface temperature of the cylinder is 667 Kelvin. And that is simply coming from our derived expression of the rate of heat transfer through a cylindrical element with internal heat generation. Now that we have the surface temperature determined, we can now use this value to be substituted in our temperature profile equation that we have derived earlier in order for us to determine the value of C2. If you'll remember, in our derived temperature profile, we were not able to solve for the value of C2 because we were not given any numerical values. But in this problem, we can now solve for C2. So let me first erase some of this stuff and we can proceed with the temperature profile. This equation, T is equal to negative Q dot R squared all over 4K plus C2, was our derived temperature profile in our previous derivation. Now we can use the boundary condition at the surface of the cylinder to determine the value of C2. So we say, for our boundary condition, at R is equal to 0.1077 meters over 2, this is the actual radius of the cylinder, meaning our position is at the surface of the cylinder. The temperature is equal to the surface temperature, which is, from what we have determined earlier, 667 Kelvin. Now we can substitute the value of R and surface temperature to our temperature profile along with Q dot and the thermal conductivity in order for us to determine the value of C2. Substituting, we have 667 is equal to negative 51.7 times 10 raised to 6 times R squared, that's 0.1077 meters over 2, quantity squared, over 4 times thermal conductivity, 33.9 watts per meter per Kelvin. And that is plus C2. From here, we can determine the value of C2. And once we determine the value of C2, our temperature profile is complete. So this becomes 667 plus, we transpose everything to the other side. That is 51.7 times 10 raised to positive 6 times 0.1077 over 2 quantity squared over 4 times 33.9. C2 is 1772.6. What's the unit of C2? C2 should be in Kelvin for the dimensional homogeneity of the equation. Okay, now that we have C2, we can now finalize our temperature profile. It is now T is equal to negative Q dot over 4K times R squared plus C2. Substituting the given and the value of C2, we have T is equal to, the collection of terms Q over 4K is 51.7 times 10 raised to 6 over 4 times 33.9. That is negative 381268 times R squared plus C2 1772.6. Okay, this is our final temperature profile. So we are done with the temperature profile and the surface temperature. The last one that we have to find is the maximum temperature of the cylinder. For the maximum temperature of the cylinder, we simply have to take the first derivative of the temperature profile with respect to R, equate it to 0, and then solve for the values of the maximum temperature and the position at which the maximum temperature occurs. So let me first erase some of this. Okay, taking the first derivative, we have dt over dr is equal to negative 2 times 381268 times r. This is our first derivative, and we equate it to 0 for maximization. So if this expression is equal to 0, we can immediately see that r is equal to 0. This is the position at which the maximum temperature exists. So how do we interpret R is equal to 0? We say that this is at the center of the cylinder. Okay? Next, you have to substitute R is equal to 0 to our temperature profile in order to determine the maximum temperature Tmax. So Tmax is now, if R is equal to 0, the first term cancels, then we have the maximum temperature as 1773 Kelvin. That is how we determine the maximum temperature. So we now know that the maximum temperature exists at the middle of the cylinder and it is at 1773 Kelvin. If we go back to our equivalent resistance diagram, you can now see the flow of energy. It starts at the center of the cylinder, that is at 1773 Kelvin, and then you go through conductive resistance, which is the cylinder itself. So the temperature goes down to 667 Kelvin at the surface, and then you go through another resistance, which is via convection, such that the surface temperature remains at 360 Kelvin. You now see that the flow of energy is from the center of the cylinder up to the outside surroundings. Okay, that's the end of this part of the lesson. Please proceed to part 2 of our lesson where we will be discussing unsteady state conduction. Thank you for watching, keep practicing, and as always, keep safe.